Right, yesterday we started talking about acids and bases. Of course. Yesterday we started talking about acids and bases, and there was a throwaway line right at the beginning of the first slide that I actually highlighted that I want to talk more about today. The line basically said pH does not go from 0 to 14. You guys remember that at all? When you guys learn about pH in grade, I don't know, 9 maybe? Whenever you first learn about pH, you learn that like anything above 7 is a base, anything below 7 is an acid. But you usually learn that it goes from like 0 to 14 or 1 to 14 or something like that. That's actually not true. It can go above 14 into the 15 range, and it can actually go as low as the negatives occasionally. My goal today now is to spend a lot more time talking about where those pH and pOH numbers actually come from. pH and pOH, those, actually, quick aside here, you guys have heard of pH before, right? Have you ever heard of pOH before? Okay, maybe I should start with that then. H stands for hydrogen. Hydrogen is kind of a key component in most acids. OH is therefore going to stand for hydroxide. Hydroxide is the key component typically in bases. Does that make sense? So whenever I talk about pH and pOH, I'm actually kind of talking about the same thing, except one is a scale that kind of refers more or less to acids, and the other one is a scale that refers more specifically to bases. Does that make sense? You know what, actually, why don't I skip ahead? Can you guys find a slide that looks like this one right here? I know it's way down in the future here, but maybe I should start with this. On a pH scale, low numbers are acidic and high numbers are basic. A pOH scale is rarely used, but if it is used, it's the complete opposite. If I give you a pOH that's really low, then it's a base. And if I give you a pOH that's really high, then it's an acid. Does that make sense? It's like an evil doppelganger. Like I think of like the, here's the pH scale, and then here's the pOH scale. It's the exact same guy, except he has like an evil mustache. That's what pOH is. So if I told you that like a pH of 4 is an acid, a pOH of 4 is actually a base. Does that make sense? So like they're just opposites of each other. We just normally work with pH because it's easier just to pick one of the scales to work with. So I'll talk more about that maybe when we come back to it. You know what? Actually, let's start with this slide right here. I have this tendency just to teach as it comes to me. So, yesterday I talked about a weird property of water. Maybe this is a good place to start. Water does not actually just sit there doing nothing. If I had my water bottle right here, there are actually hydronium and hydroxide ions in my water. They are very rare. Do you guys remember how rare? I said it on here. 2 times in a billion. 2 times in a billion, water has this ability to break apart into H's and OH's. Do you guys recall that from yesterday? That's actually a reason why water has a pH. Because you might think, well, okay, water is neutral. Why should neutral things have a pH? Well, the truth is that water actually has a little bit of acidic content in it. And water also has a little bit of basic content in it. It has a little bit of H, 1 in a billion, has a little bit of OH, 1 in a billion. So collectively, 2 out of every billion water molecules have actually split apart. Does that make sense? They will then come back together, and another one will split apart. And then eventually they'll come back together, and another one will split apart. Does that make sense? But on a molecular level, water actually falls apart, which is what causes there to be actually a concentration of H3O, of hydronium, or a concentration of OH minus hydroxide, which is why water actually, neutral stuff, actually goes on the pH scale. Okay, let me go back to this slide here then. New definitions of acids and bases. If something is a neutral solution, it actually has acid content. which seems weird. You're thinking, okay, hang on, neutral things should not have acids in them, but they do. Slight amounts. Does that make sense? And it has to be exactly this number, 1 times 10 to the minus 7. If it has that exact concentration, 1 times 10 to the minus 7, then it's neutral. This, by the way, is the concentration of 1 in a billion. You know how I just said it was 2 in a billion? Why did I just say 1 in a billion instead of 2? What's the other 1 in a billion? The hydroxide. Does that make sense? So this concentration is actually 1 part per billion, basically. If something that is acidic, it has a hydroxide concentration higher than that. So therefore, your H3O concentration must be greater than whatever neutral would be. However, if you're basic, it's actually going to be less than that concentration. Does that make sense? One more time from the top. Even water, something we think of as neutral, actually contains hydronium particles in it, things that we consider to be acids. They are rare. Water, which we've defined as being neutral, like by definition we're calling water neutral. Water actually, 1 time in a billion produces a hydronium, and the other time in a billion produces a hydroxide, which basically then can come back together and become water, and another one breaks apart. We're good on that concept? Based on that, 1 part in a billion means that the H3O concentration of water is this, and that's considered neutral. If you have extra hydroniums than water, then you're acidic. If you have fewer hydroniums than normal, then you're a base. By the way, if you have fewer hydroniums than normal, it must mean that you have, like, if you have more of this, or if you have less of this, this must mean you must have more hydroxides instead. Makes sense? It's like a ratio almost. If you have more H3O, you must have less OH. Or if you have less H3O, you must have more OH. Does that make sense? So on like a sliding scale, if I use maybe this picture again here, maybe this picture is a good one here. Right here in the middle, you're going to have some H's and you're going to have some OH's. And if the proportion of them is exactly equal, it's neutral. If you have more of one, you have less of the other. If you have more of that one, you have less of. Does that make sense? Okay, cool. Okay, let's get to like what we do with this then. I feel like I'm saying the same thing over and over again. Okay, we'll go to this slide here. Sorry that I jump around. See why I give you notes? I can't teach in a linear fashion. I just, whatever. Okay, pH. I would like you to know this. pH is actually an abbreviation. It stands for powers of hydrogen. I think that's one of my test questions, just so you know. Know that. pH stands for powers of hydrogen. The long and short of it is that powers refers to exponents. You guys know, like in math, how if you have like a power, it's like up in the corner there. Okay. We have a formula then that is going to look like this. Write this down somewhere. And then I'll show you how to use it. But yeah, put it in your data booklet. This is the formula, which is why we called it pH, powers of hydrogen, because right up here in the corner, this is supposed to be an exponent, by the way. This is like 10 to the power of negative pH. Like this is an exponent. Let me give you the example I have written here first. Let's say your hydronium concentration was 1.0 times 10 to the minus 2. They decided then to say that the pH of this was 2. The reason why is that the power up here, the exponent, was 2. Does that make sense? Let me do a different example. Let's say that it was 1.0 times 10 to the minus 3. What would the pH of the solution be then? 3. Let's say it was 1.0 times 10 to the minus 4. The pH of that solution would be... Okay, let me go back a slide here. The earliest definition I gave you here then would be neutral is actually 1.0 times 10 to the minus 7. What's the pH then? And what's the pH of neutral stuff that you always knew before this? Does that like come full circle a little bit? Okay. So that's how pHs are actually derived. Whenever we talk about pHs, pHs actually refer to what is this little exponent up here. And so if the exponent is a little number like 1, 2, 3, or 4, it means it's an acid because the concentration is like 0.01 or 0.001. That, although those numbers are still less than like small numbers, those are actually fairly acidic. Let's say that the solution was 0.00000000001. Well, this is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 1 times 10 to the minus 12. So that's a pH of 12. Is that actually acidic anymore? No, it's so far past the breaking point. Remember how I was kind of saying like 7 is kind of equal for both? We're so far past the breaking point that we don't even have acid. What we actually have instead of acid is base. Does that make sense? So let me try another example here. Let's say I told you the pH was 3.75. Well, using that formula I just showed you, I can actually tell you how much acid concentration there would be, how much H3O concentration there would be. You'd go 10 to the power of negative pH. So you'd go 10 to the negative 3.75. Let's just grab a calculator here. So you'd type in 10. You'd use the little like arrow up button. You guys know that one? Yeah. And then negative 3.75. This is 1.78 times 10 to the minus 4.
So then pH is 4.
Well, okay, so that exponent right there only works if this number right here is exactly 1.00. Does that make sense? So the pH is approximately 4 due to that number right there, but the pH was actually 3.75 because it wasn't 1.00. It was actually 1.78. Is this bigger than 1.00 times 10 to the minus 7? Yes. Because this number right here is 0.000178. That's acidic. This is what water would be, and that would be 0.0000001. Which one of these numbers is a bigger number? This one up here is bigger. It leads to a kind of a weird scenario there where bigger means you want a smaller exponent. I'll say that again. Bigger numbers technically have smaller exponents. Because if I gave you something that was to the power of minus 1, and I gave you something that was to the power of minus 4, the one that's to the minus 1 is actually bigger than the one that's to the minus 4. Does that make sense? This is why things are more acidic when the pHs are 1, 2, and 3 than they are when they're 4, 5, and 6, and 7. Does that logic make sense? Let me say that one more time because that's such an integral part of what happens here. Let me just make up another example even. New page. Let's say that I gave you a pH of 6.2. Acid or base? Strongly acid? It's kind of approaching neutral, but it still should be more acidic than neutral. Does that make sense? So using the new formula I showed you, to find out how much H3O concentration there would be, you'd go 10 to the minus 6.2. So if you guys have a calculator, help me out here. What does that give you in your calculator? Okay, we'll stop there. Okay, so that means 6.3095 times 10 to the negative 7. Okay, this exponent right here is not exactly the pH because this number right here is not 1 exactly. But it's kind of close, right? Like this was a 6.2, that's a 7. It's basically in the ballpark. Does that make sense? This number right here, is it bigger or less than 1.0 times 10 to the minus 7? Because this is what we've defined neutral to be. Is this number here bigger than that number or no? This is 6.3 to the minus 7. This is 1.0 to the minus 7. This one's a bigger number. Does that make sense? Is it a lot bigger? Not a ton. It's a little bit bigger, right? If I were to write these numbers out, this number is 0.00000063095. And this number here would be 0.0000001. 0, 0. Which number is bigger? The top one. Does that make sense? Is it a lot bigger? Not a ton. Like, it's a little bit bigger. That's why we define this one as neutral, and then this guy here would be considered an acid. Let me try one more. Let's say I gave you a pH and I made it 8.3. Okay, pH of 8.3 we know should be a base, correct? Okay, so let's try to prove it. 10 to the minus 8.3. What would that give you? Sorry, I'm just doing 8.3. Anybody got 10 to the minus 8.3? Somebody? Anybody else get that? Just try it. I'm not going to yell at you if you get it wrong. I just want to make sure that that's right. That's a -9, I think you said. You got that? Okay, so what does this number mean then if I write it out? It means that it would be 0. Okay, let's count them out. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have chosen this number right here to be considered neutral. Why did we choose that number to be considered neutral? Because that's the concentration of H3O one time out of a billion. Does that make sense? Is this number bigger or less than that number there? Less. And therefore, because it's less than that, that's why it's a base. Because if you think of that sliding scale, if you have less H3O plus, it means you must have more hydroxide. Does that make sense? So if water is even for both, if I have less hydronium, then I must have more hydroxide. Or for this one right here, because this number is a bigger number, I must have less hydroxide. Jimmy?
In the first example, like just after our notes, where did the 4 come from? Like the power of the 4, is that just by hydroxide?
Oh, like, yeah, in your calculator, if you type in 10 to the power of minus 3.75, this is what your calculator spits out. Does that make sense? What should happen is whatever your pH is, this should be very close to the exponent. The only reason it won't be the same is that this number right here is no longer 1.000 repeating. So that basically in a nutshell is how the pH scale was kind of developed. It's hard to kind of work with, in my opinion, because you guys already learned about pH probably at some point. And now I'm kind of going into detail as to how it works. So the questions I'm going to ask you, though, are not usually all that hard. Like, really, we just need to use the formula I gave you. And if I give you a pH, now tell me a concentration. So, here's what that means then. You know how I told you yesterday the pH scale usually is shown from 1 to 14? It actually can go below that. Let me show you an example here. Let's say that the pH was equal to -1.1. I know that seems odd because up until today or yesterday, you've never heard that pHs can go into negatives. But like, let's say that pHs could actually go to something like -1.1. How would that work in your formula? Okay, so then it would be 10 to the minus 1.1. Okay, so help me out with the calculator. What is 10 to the positive 1.1? Okay, what we just calculated here was a concentration of H3O+. What do we measure concentration in?
Moles per liter.
What have I told you is usually the cap for most solutions? How high can the most concentrated solutions usually get to? Yeah, maybe 15, 18. Is 12.58 a reasonable concentration? Is that plausible? Yeah, like we're talking super highly concentrated solutions. But a super highly concentrated solution might actually have a pH that's actually in the negatives. Does that make sense? It is so concentrated that it's actually gone off the scale. Does that make sense? Okay. Let's try the opposite. Let's say that we give you a pH that's beyond 14. So that would be like, I don't know, 15, pH equals 15.3. What does that mean you'd do? You'd go 10 to the minus 15.3. Ten to the minus 15.3. So that just means that your concentration is 0.0003, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is this a concentrated solution? No, it's really not a concentrated solution at all. This is like as unconcentrated as you can get. Now think of my sliding scale. If on the first example, all you had was acid, on this example here, you have like no acid. What does that mean? It's all base. This must be a solution then that is highly basic. Does that make sense? It is a super concentrated basic solution. Does that make sense? I hope that works. Here's the second formula then. If we have a way to calculate a concentration based on the pH, we also need a way to go backwards. It involves using a button on your calculator that I won't explain to you in math until next year, sadly. It kind of sucks. But it's this button right here. It's called log. You guys find that button? It's not hard to use. It's just, we talk about it mathematically in grade 12. So here's the second formula then. Let's say that I give you a pH. Let's take a pH of 7. Well, actually, no, let's say we want to find a pH. Okay. Neutral things are supposed to be 7 for pH, right?
Yeah.
But the concentration of neutral things was supposed to be 1.00 times 10 to the minus 7. Does that make sense? That's supposed to be something that's neutral. So what I want you guys to do then is take negative log and then type in your calculator 1.00 times 10 to the minus 7 and like close a bracket around that and see what it tells you. So negative log, open a bracket, 1.00 times 10 to the minus 7, and then close the bracket. Yeah. So what we've done here is this is the concentration of a solution that we have defined as neutral. And based on this formula, it tells us the pH of that solution is 7.
Okay, so how do we know what number to put as your small?
I just told you to use this one here because I happen to know that that was what neutral was going to be. Why don't I do another example then? Let's say I gave you a solution that was 3.45 times 10 to the minus 3 moles per liter. But before I go on, what sort of pH do you predict this is going to be? Acid, base, or neutral? It's going to be an acid. Write this number out. This number would be 0.00345 moles per liter. How does that number compare to 0.0000001 moles per liter? Bigger or smaller? Way bigger. Exponentially bigger, actually. Does that make sense? So if this guy has been defined as neutral, I'm going to predict this guy is going to be an acid. Does that make sense? I can also make another prediction. I bet you the pH is going to be roughly in the 3 range, based on that 3 number there. But to find its exact pH, I'm going to go negative log of that number.
Oh, so you'll give us the 3.4.
Yes, I'll have to give you a number to work with. Does that answer your question? Yeah, I'm just pulling random numbers out of the month.
I was just confused because I didn't know how you put it.
No, I'm picking random numbers.
Okay.
So, anybody type that in? Negative log 3.45 times 10 to the minus 3?
3.46.
All right, that'll work. Does that fit with what I predicted? Yeah, I mean, this 3 right here meant that I thought the pH should be in the near 3 range. 2.5, that's kind of close to 3. I also wrote this number out, and then I wrote it out next to what has been defined as neutral, and saw that, yeah, this number here is way bigger than neutral. So again, if neutral means equal H and OH concentrations, and we have way more acid, it must mean we also have way less base. So this should definitely be acidic, and then the pH number that it spits out is definitely acidic. Does this make sense?
Yeah.
It's a lot deeper in terms of pH than you probably have ever seen before. Because normally I would say that kids think that pH defines whether something is an acid or base or not. And it's actually almost the opposite. This number right here, we chose that to be neutral, and then we compared acids and bases to that. And it just happens that that's how the pH numbers work in comparison. Does that make sense? So they didn't just choose 7 to be the pH number for water. This happened to be the number, and it actually produced a 7. So that's why 7 is the neutral number. Okay, so let's do some examples here. Okay, before I do the examples here, if I ask you to find a pOH, use the exact same formulas, except make them hydroxide numbers. Does that make sense? So like pOH is just the negative log of a hydroxide number. And OH minus is the 10 to the minus pOH. So like you do the exact same steps, it's just you use a different concentration. Remember, as one goes up, the other goes down. Yes.
So the pOH formula would just be 10 to the pOH.
Negative pOH, yeah. It's like the exact same formulas that I just showed you before. It's just rather than having an H right here and an H right here, use OH.
And we don't need the 1.0 or anything like that in front. Like it's just, then we'll write it as like, okay, I understand.
Let me try the 2 examples I've got here. Here's a hydroxide ion concentration. Find me the pOH. So how do I convert a hydroxide ion constant to a pOH? Which formula that we just kind of talked about would help with that? Find me a formula that gets pOH equal to something. Go back in your slides and find one. Negative log OH minus concentration. So we need to negative log an OH minus concentration. Do we have that concentration? Yeah, I gave it. I have to give you a number somewhere, right? So here is the hydroxide concentration. So negative log this number. That's it. Honestly, that's it. That's all you gotta do. Negative log that number. Well, okay, so we could have written this then as 3.6 times 10 to the minus 3. Does that make sense? Because I moved it over 1, 2, 3 times. So I'm going to expect this pOH to be somewhere in the 2 to 3 to 4 range by the time we're done, based on it being a minus 3 up here. Okay. Does that make sense? That's the pOH. Was this an acid or a base? Base. Does that make sense? This is a twist on this one here. Normally a low number means it's an acid. But this is not a pH number, it's a pOH number. So therefore this must be a base. That makes sense? I think I also knew that. If you have a hydroxide ion concentration, think of that like scale I had here. If you have a lot of hydroxide, it means you must not have a lot of hydronium. So therefore that must mean you have a base. Okay, one last thought here on this question here. We gotta get sig digs right. How many sig digs did this number up here have? 2. Okay, sig digs for pHs and pOHs work a little differently here. This appears to have 3 sig digs. It does not. It only has 2 sig digs. This number right here, the one before the decimal place, does not count as a sig dig. And I actually have a good reason why. This 2 right here essentially is telling you how many zeros there were right here. There were 2 zeros right there. Did these zeros right here count as sig digs? No. So therefore, this 2 before the decimal place does not count as sig digs. What ends up happening then when you do pH sig digs is you often get an extra digit. So this right here only has 2 sig digs because numbers in front of the decimal don't count. Yeah.
Even if there's like 2 numbers above,
Sure, it still doesn't count. Let's try another example here. Let me try another example. Let's say I negative logged 0.0000000000012. This one should only have 2 sig digs. But I need someone to get me the value first. So 0 and then 3 zeros, 3 more zeros, 3 more zeros, 1 more 0, then 1, 2. What'd you get? Anybody negative log that one yet? Okay. Okay, and that's actually the answer we'd use because the 10 refers to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros in front. That's what the 10 refers to. But these zeros in front would not have counted as a sig dig. Does that make sense? So this 1 and this 2, they provide us sig digs. That's where the 2 sig digs comes in. By the way, there are no units for pH. So even though the units for this should have been moles per liter, the units for pH, there is no units behind it. So maybe the only time where I let you write down a number in chemistry class and you don't have to have a unit afterwards. Does that make sense? Okay. One last example, then I'll do a summary, then we can take a break here. Let's say that I gave you a solution with a pH of 3 and a solution with a pH of 6. I want to ask you, how much more hydronium is there? Okay. What's the formula to find hydronium? Anybody remember off previous slides a formula that gets us hydronium concentrations?
10.
Good, 10 to the power of negative pH. That's a formula we can use. So let's go 10 to the minus 3. I think what's going to happen is that's going to be like 0.001, because that'll be moving it over. Wait, hang on. Let's make sure I have that right. 10 to the minus 3 would be, 0.001. Does that make sense? And let's also try to do 10 to the minus 6. My calculator says 1e minus 6. But like that means 0.1, 2, 3, 4, 5, 6. The point I want to make here is which one of these numbers is the bigger number? Yes. This one right here is the bigger number. This guy right here is the smaller number. Does that make sense? In pHs, it's weird. You'd actually, to get a bigger number, you want the pH to be lower. Right? A pH of 3 or 2 or 1 has less zeros in front of it, and that makes it a smaller number. So then my question is, how many times bigger is this number than this number? Okay. Let me do a different example. 10 and 2. How many times bigger is 10 than 2? What did you do to solve that in your heads? You did 10 divided by 2. Take the bigger number and divide the smaller number. Do the exact same thing here. Take your bigger number and divide your smaller number. Just make sure that you get which one is the bigger number and which one is the smaller number.
Like, we divide the
Yeah, we want to divide these numbers by each other. So what happens when you take 0.001 and you divide by 0.00001? 1,000 times bigger than. If you can wrap your head around the weirdness of like lower numbers are actually bigger numbers, if you can wrap your head around that, that's probably the hardest thing about pHs. So let me give you a quick summary, then we'll take a break. You guys knew stuff about pH before I talked to you today. I know you did. But my thought process is you probably were under the impression that we randomly chose 7 to be neutral, and then everything above and below was that. That's really not how this developed. It really developed that water was chosen as neutral. I mean, that kind of makes sense, right? But we didn't just pick 7. Why didn't we pick 19? Why didn't we pick 3? Does that make sense? The reason why is that water breaks apart 2 times in a billion. And if we calculated the concentration, it was 1 times 10 to the minus 7. Does that make sense? Anything above that made it acidic. Anything below that made it basic. Does that make sense? Kind of like that sliding scale there. Finding those concentrations then, if we wanted to actually make a pH, we did negative log of that concentration, and it gave us a pH. So when you negative log that 1 times 10 to the minus 7, it gave you 7. If the number was a bigger number, when you negative log it, it actually gives you a number like 6, 5, 4, 3, or 2. If your hydronium concentration is actually really small, then it actually produces a bigger pH value, like 8, 9, 10, 11, 12. And it doesn't just end at 14 or 1. It is actually possible to go into the negatives. You can make a solution so concentrated that it's so, like if you have your break-even scale here for water, it is so much up here and down here for this being acid and this being base, that it's that concentrated that the pH scale actually goes in the negatives. Actually, one more point I should make here. Even in the most concentrated of acids, you will actually still find a small presence of hydroxide. Let's say that one more time. Even in the most acidic of acids, you will still find hydroxide. Just like that sliding scale. If water is like this, if you have an acid that's way up here, you will still have a little bit of hydroxide left. Does that make sense? All it means is that some of your water molecules, some of them have still broken apart, and you'll still find a random hydroxide sitting there. Does that make sense? So it fundamentally changes the way you think of things, because H3O, or H, I guess, and OH minus are actually found in all compounds. The question is, how do they relate to each other? Even is neutral, acid, base. Does that make sense? Okay, what I need you guys to be able to do then is basically 2 formulas. One of the formulas will look like this, where you solve for a pH or OH, or the other formula is this, where I ask you to solve for a concentration. Honestly, they're really easy to use. You just need to know which one to use, that's it. All right, questions, comments, concerns, conundrums, curiosities, complaints, criticisms?
No.
You guys good? Okay. Wait, take a 5-minute break. When you come back, can you guys make sure you finish your labs? And then for the next couple of days, like the rest of today, tomorrow is a work day. I'd say work on your assignment. Or if you really want to practice some textbook questions, here's a few textbook questions. But the next little bit of time is work time to finish stuff.